Hello everyone, my name is Zhaijie Wang, a PhD student from Tsinghua University, supervised by Professor Cai. The talking I'm going to share is about McPAT-Calib, a microarchitecture power modeling framework for modern CPUs. It's my honor to do this presentation. I hope that our work can promote the development of CPU design and power modeling. The presentation will be given by the following aspects. First, I will introduce the basic background. For the second part, I will give preliminaries and problem formation. For the third part, I will introduce McPAT-Calib in detail. Finally, I will show the evaluation results. With the slowdown of Moore's law and the ending of Dennard scaling, power consumption has become the main constraint limiting the performance of modern CPUs. In industry, it's necessary to conduct accurate power performance trade-off at the early design stage to ensure excellent CPU design. At the same time, the design space of modern CPU is becoming larger and larger. Designers need accurate modeling tools for extensive design space exploration and optimization. All of these make power modeling face great challenges and put forward higher requirements for power models, such as modeling speed, accuracy, and generality. Speed not only refers to the modeling speed of the model itself, but also the time required for the entire modeling flow. Accuracy means that it must be able to accurately model complex CPU microarchitecture and advanced technology nodes. Generality refers to the power model's ability to model different CPU designs or workload programs. In fact, there are already many power models. The most accurate power models are commercial tools. For example, Primetime PX. Designers need to obtain get netlist and simulation results to analyze power, and the entire flow is extremely time-consuming. Academia has also proposed many modeling methods for different design stages. At the gate or RTL level, power models, for example, Granite and Primal, are built based on simulation traces using feature engineering and machine learning methods. However, these models require netlist design and simulation, which is also time-consuming. More importantly, these models are design-specific and cannot model unknown CPU design. At a higher microarchitecture level, power models use microarchitecture design parameters and event statistics for power modeling, which have the fastest modeling speed. However, these models are difficult to capture hardware details, resulting in low accuracy. Analytical power models, for example, McPAT, are general and directly usable, but the modeling accuracy is very low. PMC-based runtime power models, for example, ICCAD 17, can also be used through transformation, but they are design-specific and cannot help CPU design. By comparing these models, we can find that it's difficult to balance modeling speed, accuracy, and generality. These models are difficult to use in the early design stage. Among these models, McPAT has gained popularity due to its ease of use and readiness. It uses hierarchical analytical modeling from the technology level to the circuit level, and then to the architecture level. McPAT allows designers to model power using only design parameters with event statistics without RTL design and simulation, and has high modeling speed and generality. However, there are two drawbacks that make it difficult for McPAT to help the design of modern CPU. First, the modeling accuracy is very low. Second, McPAT lacks support for advanced technology nodes. Next, I will introduce the definitions of power modeling. Generally, the total power can be expressed as this equation. including dynamic power and leakage power. The first expression is a well-known transistor-level power definition. This is very expensive for CPU design. More importantly, we cannot capture so many hardware details at an early design stage. In order to more quickly model the power, we try to model power at a higher level, microarchitecture level. At this level, the dynamic is the sum of functions of event statistics, and the leakage is a function of design parameters. Then we give two definitions. The first is microarchitecture configuration. This refers to a CPU design characterized by a set of microarchitecture design parameters, such as fetch weights, decode weights. The second is benchmark, which refers to the workload executed on the target CPU. Even on the same CPU design, different benchmarks will have different event statistics and power consumption. Therefore, the microarchitecture power modeling problem can be defined as: give a set of CPU configurations C and a set of benchmarks B. The objective is to model the power PIG of a benchmark BG running on a configuration CI. In this work, we use this file boom as target CPU. This file is an open source RSA that has received strong attention and support. Boom is a family of order RISC-V designs, and also the fastest open source core. Thanks to parametric microarchitecture design, designers can obtain different boom by configuring the core with different parameters as shown in the left figure. In addition, boom has been integrated into ChipYard, an automatic design flow. It's convenient to complete RTL design and VLSI flow of different boom. This page shows the power modeling flow. When the configuration and benchmark are given, a commercial flow is shown by a dotted line. RTL design and logic synthesis are required to obtain a gate-level netlist, and then gate-level simulation and power analysis are performed. We use this flow as a golden tool to obtain the ground truth of power. The flow of our framework is shown by a solid line, which can complete power modeling in a few seconds. G5, an architecture simulator, is used to complete a simulation of boom to obtain detailed event statistics. Then, McPAT-7 is used to complete the fast preliminary power modeling. Finally, ML methods are used to calibrate dynamic and leakage to obtain more accurate results. We first introduced internal improvements to McPAT. Unlike ML-based models, the analytical power model depends on technology parameters. The original McPAT does not support advanced technology nodes. Our target is 7nm FinFET PDK ASEP7, and the key parameters are shown in table. We also obtained some parameters through scaling. McPAT also uses some empirical coefficients, and we adjust these coefficients to reduce modeling errors. We also made some microarchitecture modifications to support modeling for boom. Through these improvements, we support the modeling of 7nm boom with an error of 13%. In fact, an internal improvement of McPAT is a very dirty engineering work that requires in-depth hardware analysis. Therefore, we hope to use machine learning calibration technique to further improve accuracy. To provide more details, we try to calibrate leakage and dynamic separately, and then take the sum to get total power. Leakage is uniquely determined by the CPU design and will not change with different benchmarks. Therefore, we only calibrate the the average of leakage for the same configuration. This will cause the number of samples to be greatly reduced. So we only choose two features, that is, the modeling results from McPAT, core leakage and core area. Unlike leakage, dynamic is closely related to configuration and benchmark. Even samples under the same configuration, dynamic may still vary greatly. Therefore, the dynamic of each sample must be accurately modeled. We take McPAT results, event statistics, and design parameters as dynamic modeling features. It's also an important contribution of this work. Due to the selection of extensive features, we achieve better results than previous work. This figure shows all the dynamic modeling features. Shown in blue are features from McPAT results. Shown in orange are the microarchitecture parameters of BOOM. Shown in green are event statistics obtained by GIMP5. As shown in figure, the correlation between most features and the dynamic target is very high. However, the use of such a large number of highly correlated features will bring about a challenge, that is, mathematical linearity, which refers to the correlation between features, can be measured by width. To find the width of a feature, an OLS regression model can be built, which predicts this feature using the others. Then the width is shown as equation 2. Generally speaking, a width over 10 indicates strong mathematical linearity. As shown in the figure below, this problem can be ignored because it will lead to high model complexity and lack of stability. More importantly, it will cause the power model to overfit on existing samples, fail to model unknown configurations or benchmarks. So, we use automatic feature selection to select a small number of features that can reflect different configurations and benchmarks. First, we filter out some features with low variance because these features cannot provide enough information. This method can reduce the search space. Then, we use a greedy strategy to sequentially select the current best feature obtained by cross-validation until the number of selected features reaches the set value. This selection algorithm is simple but effective. The next problem should be solved is non-linearity. When complex workloads are executed on a CPU, the relationship between feature and the resulting dynamic is nonlinear. We use the advanced nonlinear model, XGBoost, to directly solve this problem. XGBoost is widely used to achieve SOTA results on many machine learning challenges. It's a train-in-sample model use key additive functions to predict the output. To learn the set of train functions, the following regularization objective is minimized. Here, L is a loss function that measures the difference between the prediction and the target. The second term, omega, generalizes the complexity of the model. Now, we can get a nonlinear power model with strong generalization ability. Now, we know how to build a power model. First, use GIMP5 to complete simulation to obtain event statistics, and then use McPAT-7 for preliminary modeling. After feature extraction, a leakage calibration model and a dynamic model are built. However, we still face a challenge, that is, a large number of labeled samples are needed to train a calibration model. For power modeling, labeling samples is time-consuming and costly. Contrary to getting a label, It's easy to obtain features and only takes a few seconds. Therefore, can we select the most beneficial samples to label based on the easily available features under a limited budget? The answer is active learning. AL is a technique to reduce the demand for labeled samples by selecting the most useful ones to label instead of random selection. We can use pro-based sequential AL algorithm. First, obtain the features of all samples to form a sample pool. Then, each time, the most useful sample is selected from the pool to be labeled and added to the training set. Our pre-clustering sequential sampling algorithm can be divided into 3 parts. First, we select some initial samples to build a basic model. Here, to ensure a diversity of samples, we complete the initial selection through clustering. Then, use the sample query strategy for sequential sampling. Our goal is to increase the diversity of samples in the input and output spaces. Suppose there are k-labeled samples. We calculate the minimum product of the feature distance and the label distance between the unlabeled sample and each labeled sample. We select a sample xn with a maximum dnxy to label. Finally, the sampling stops when the number of labeled samples reaches the budget. This page shows the AL sampling algorithm. Due to the limited time, it will not be explained in detail. To confirm the effectiveness of our framework, we conduct a comprehensive evaluation. We use up to 15 typical BOOM configurations and 80 commonly used benchmarks. In this way, we can get 1,200 samples, enough to evaluate the generality of power models. Power modeling is a regression problem. We use mean absolute percentage error, MAPE, and R-square as metrics. As an analytical power model, McPAT-7 can directly model all samples without training. So, the preliminary modeling results are shown in this figure, where MAPE is 13.02%. Then, we use ML methods to calibrate leakage and dynamic. We compared 15 models, and the results are shown in table. The second column is the leakage results. The third to fourth columns are dynamic results using all features. The fifth to seventh columns are dynamic results after feature selection. We can see that most models cannot obtain good results using all features, and feature selection can effectively improve accuracy, especially for linear models, because it can overcome the adverse effects of multilinearity. In addition, XGB Boost obtained the best modeling results. Next is the modeling of total power. Here, we use polyclonal SVR as a leakage model and XGB Boost as a dynamic model. To evaluate the accuracy and the generality of power model, we designed 3 cross-validation strategies. The first, treats all samples as equal and perform 15-fold shuffle splint cross-validation, and MAP is 3.38%. The second is to perform splint validation according to configuration to simulate the situation where models are unknown configuration. Therefore, we performed a 15-fold CV and MAP is 5.22%. In the same way, we performed a 20-fold cross-validation according to the benchmark, and the MAP is 5.96%. The page shows the modeling results of different configurations and benchmarks. It's easy to see that the modeling accuracy of McPAT-Calib is much higher than McPAT-7. Then, we compared our framework with previous microarchitecture modeling methods, including the design parameters-based model, HPC7, the event statistics-based modeling methods, TCAD17 and TCAD20, and the McPAT-based calibration method, PowerTrain. As shown in this table, the accuracy of McPAT-Calib is much higher than previous work. Finally, we evaluate the AR sampling algorithm. 15-fold config splint CV is performed, and a certain ratio of samples from training set to be labeled for each validation. The results show that our sampling algorithm can effectively reduce the demand for labeled samples. When the number is reduced by 50%, the accuracy loss is only 0.44%. When the ratio reaches 60%, the modeling error tends to converge. This page is a summary of our work. First, we summarize the reasons why McPAT-Calib is effective. What followed is some prospects. We will use the same ideas to achieve performance or area or timing modeling, and we'll also try to use these models to help the DSC of the CPU. These are all my presentations. Thank you.